Welcome to ECE 6520. Today is our lecture 28, which is our last lecture of this semester. Okay, and so let's briefly review what we have covered in our lecture 26, right? Because our last lecture covered homework 5. Okay, so in lecture 26, we finished talking about the rate distortion theory. Basically, we have three topics there, which is Arimoto-Blackwood algorithm, sometimes called this Blackwood-Arimoto algorithm, and the separation theorem, and the parallel Gaussian sources, which is the counterpart of the parallel Gaussian channel in the rate distortion theory. Okay, and let me move my picture here. So basically, the Arimoto-Blackwood algorithm. The reason we have this algorithm is that we have seen the analytical method to compute the rate distortion function is very complicated, right? Because we need to determine the good letters and bad letters. This is a combinatorial problem, which can be very hard, right? And therefore, we want some numerical approach to compute the rate distortion function. So basically, Arimoto-Blackwood is a way to do that. The fundamentals of the Arimoto-Blackwood algorithm are the following two lemmas. So the first lemma basically tells you that so this Ry to minimize this relative entropy is given by this form. In other words, if we plug this in here, then basically what we are getting is the mutual information, right? And we know that the mutual information basically is a quantity that we want to minimize for the rate distortion function. Therefore, we further minimize this mutual information by px hat given x, then we can get the rate distortion function, right? So the beauty here is that before we just have one variables, but now we have two variables, right? Therefore, it is possible to do this iterative algorithm, which means that by fixing one identity, we minimize the other one, and fix the other one, minimize this one, right? This is the basic idea of this Arimoto-Blackwood algorithm. Okay, and similarly, we can get this behavior for the channel capacity as well, where the quantity that we're trying to minimize is not relative entropy anymore. It's given by this formula, where this Rx given Y is a quantity that we want to pick, right? Therefore, we can get in this case, so instead of the minimization, so for the mutual information, we have a maximization here, okay? And therefore, by doing this, we also can get the channel capacity can be computed as this double maximization problem, right? Where we also can fix Rx given Y, compute Px, and fix Px, and then we compute Rx given Y, okay? So this is, so based on this two lemma, we could get the Blackwood algorithm and the Arimoto algorithm. Usually, for the Blackwood algorithm, we mean by to compute the rate distortion function, right? And here, basically, we start with an R0 x hat, and then so we use this formula to update px hat given x, and then by computing that, we can update our x hat again, right? So the beauty here is that so we can get the analytical updating formula at each step, right? The complexity of the algorithm should not be very high, okay? And we're gonna keep doing this until the algorithm converge, right? Very good. And the other one is, oh, by the way, so in class we also give a approach that we can only doing updating on this guy, right? So it's a mathematical trick, but you can see that if you're interested, okay? And the Arimoto algorithm is to compute channel capacity, right? The idea is identical. So by fixing Px, then we compute R, and then by fixing R, we compute Px, right? Here, there's an equal sign here, I forgot, I guess. Okay, so this is the Arimoto algorithm. Okay, very good. And and then we talk about the separation theorem. So basically, the idea here is identical as what we did in the channel capacity session, right? So here, basically, want to see what is the condition that we can passing a source to a channel, right? What are the conditions, right, with the distortion constraint of D here, right? So the idea of here, I mean, the approach here can be very simple, right? So basically, we can do this separate source channel coding approach, right? Which basically means that we're doing the source coding for the rate distortion, right? And then we can do the channel codes and then passing the signal, okay? And at the receiver side, we first decode the channel code and then decode the source code, okay? So it means so the interesting thing here is that this approach is optimal asymptotically, right? Which basically means that when k goes to infinity, and this is asymptotically optimal, right? We can show this is a sufficient and necessary condition. RD has to be less than tau times C, where tau is the ratio between the source block length and channel block length. Okay, so and so the conclusion here is basically identical as what we're doing for the source and channel separation theorem. Okay, without distortion. All right. Okay, and again, so this is a symptotic result. If we consider finite block lengths, right, things can be different, right? Therefore, it still makes sense that we're doing joint source channel coding in practice. Okay, very good. And then the last step, let me move it here. So the last topic in the rate distortion theory is a parallel Gaussian source, where we consider a number of sources, m sources, with a Gaussian distribution with mean 0 and variance sigma I square, right? And we consider the quadratic distortion matter like this, and then basically we could compute that. So the rate distortion function is given by basically something like that, right? But we need to take the maximum between each term of this guy and 0, right? Okay, and after doing this, so because we have a sum distortion constraint, right, which is basically given by this formula, so therefore we need to still need to optimize a convex optimization problem, which is given by this problem again. So we can see that this is a convex, right, and all the constraints are convex. Therefore, so we can use the normal KKT condition to solve this convex optimization problem. And basically, what we're getting is basically this guy, right? So we're getting DI. The optimal distortion for source I is given by mu and the sigma minimum between mu and the sigma square. We need to make sure that the summation of this guy is D. So that's the way we determine mu, right? Okay, very good. And therefore, the optimal rate distortion function is given by this. And we give a pictorial illustration of this algorithm there. So basically, it's called reverse water filling bit allocation, right? Which is in contrast to the water filling power allocation for the channel for parallel Gaussian channel. Okay, so okay, up to here, so that's everything that we're gonna cover for the final exam, right? So what we're going to cover today will not be in the final exam, right? But for the completeness of this course, and I will talk about this. So this is actually a very important direction or very important area in the big area of information theory. So this is called network information theory, and which by itself can be easily a very complicated class, right? Sometimes it's also called multi-user information theory. Okay, maybe let me write it down, multi-user information theory. And as we said, so it's a very big area. The idea here is that so far we have considered is one source and one destination, right? We have one retransmitter and one receiver. We could have the channel, we could, without the channel. So, but for network information theory, we're considering more than two sources, well, more than two nodes, right? So that's basically the meaning of network, right? Network usually means the number of nodes are more than two, right? Okay, and And in this class in particular, so we'll talk about a very specific topic in the network information theory, so which is the distributed source coding. Okay, and so we're gonna see in a minute that in this network we have 3 nodes, right? We have 2 sources, want to encode them, and at the receiver side, want to recover both of them simultaneously, right? Okay, very good. So in particular, so the distributed source coding sometimes is also called Slepian-Wolf coding. So these are the 2 names. Okay, and in particular, we have 4 topics to cover in this lecture. The first topic is to introduce the problem definition and talking about the Slepian-Wolf coding theorem. And the second topic is the conditional. So we're gonna show the achievability of the Slepian-Wolf coding and the converse, right? So in order to show the achievability, we need to introduce another concept of the typical set, which is called conditionally epsilon typical sequences. Right? Remember, we have covered a number of typical sequences before, right? The original typical sequences, the joint typical sequences, right? The distortion epsilon typical sequences. Here is called the conditionally epsilon typical sequences, right? And after that, we're gonna introduce the achievability of the Slepian-Wolf coding, and here it's kind of important. So we're going to introduce a new coding technique or a new random coding technique, right? So before, so what we have covered basically is to, for example, in the source coding part, we need to know the joint, we need to know the typical sequences at the transmitter side, right? And basically, we just need to transmit everything in the joint typical sequence, okay? But here it's very different, right? So we're gonna introduce a new technique called random binning, where at the receiver side, we do not need to know any typicality of the sources, right? Which is a very new technique. Okay, and lastly, we're gonna talk about the converse. So the converse here is pretty standard. There's not much new here. There's some new tricks that we're gonna use, but the idea would be identical as what we have seen before. Okay, very good. And now let's get started. So first, let's talk about Slepian-Wolf coding theorem. Okay, so for the Slepian-Wolf coding theorem, consider two sources, x and y. They have a joint distribution, pxy. So basically, the pictorial description is like this. So we have two sources. For example, we're gonna do the block coding. We have xn, and then we have yn, right? So the reason it's called distributed source coding is that we're gonna do the encoding of x and y separately without knowing each other's distribution, right? Or without knowing the joint distribution, right? So this source here, this encoder, only knows the distribution of x, and this encoder only knows the marginal distribution of y, but they have no idea about the joint distribution pxy. Otherwise, the problem is very easy, okay? And but for the decoder, right, the decoder is like the receiver receive both of the transmitted signal, right, and then it's gonna decode, right? They can observe both of them, and then they're gonna decode x, y together to get x hat and y hat. Okay, so this is basically the procedure, right? Okay. So this is basically the distributed source coding problem. Okay, and now let's write down the general, the formal definition for this problem using the information theoretic language that you have seen many, many times, right? Okay. Okay, very good. And so let this xi, yi, this pair be a sequence of ID random variables, right? We're still considering DMS, right? So therefore, it'll be ID with generic distribution, with generic joint distribution pxy, okay? And for the encoding function, so we have two encoders, right? So this guy and this guy, right? We mark this guy as, we denote this guy as F1 and denote this guy as F2, okay? So the encoding function is F1 and F2, okay, where F1 is from this alphabet to an index 1 up to M1, okay, and clearly if we use a rate to determine M1, so this equals 2 to the power of NR1, okay, where R1 is a rate for the first source X, right? And similarly, 5.2 is from the alphabet of Y, T1 up to M2. Okay, and clearly M2 equals to 2 to the power of N R2. Okay, so in particular, R1 equals to 1 over N log M1, and R2 equals to 1 over N log M2, where log is obviously based on 2, right? So this is the encoding function, right? So this is, the definition here is pretty much identical as the source coding problem, right? The single source coding problem, where we just map the source to an index and then transmit this index, right? Because the code book will be known at both transmitter and receiver. We just need to transmit the index. Okay, very good. And for the decoding function, so that is denoted by G, right? So this is G, okay. And for this function, so G is from a product set 1 to M1 to 1 to M2, right? To X and Y, the set of the alphabet of X and Y. Okay, so this is basically the definition of the decoding function. And next, let's define the probability of error. Right, as we have seen before, right, different definitions of probability error will not result in different result, right? So here we just go to the simple version of the probability error. So we just assume that the probability error basically means that the decoded signal G of x1 x and f2 y, okay, that does not equals to x in, y in, right? We just assume this is the probability of error, okay? Kind of the average probability of error, okay? And we say that a rate pair, let's say it's R1 and R2, is called achievable. So if R1 achieve R1 and R2 achieve R2 as n goes to infinity and error goes to 0, right? Basically, that's the definition. But here, in detail, in the mathematical world, it basically means that there exists an epsilon for all epsilon bigger than 0, there exists n, which is function of epsilon, right? Is a big integer. For any n is bigger than or equal to n epsilon, there exists a code, let's see, Cn, such that the rate of this code R1, so it's less than or equal to R1 plus delta epsilon, where the delta of epsilon basically means that, so delta epsilon will goes to 0 as epsilon goes to 0, okay? And R2 Cn will also be less than or equal to R1 plus delta epsilon, and overall the rate will be less than, it goes to be less than or equal to epsilon, okay? So that's basically the definition of the achievability, okay? And so those are the achievable point, right? R1 and R2. And the achievable rate region is nothing but denoted as a set of R. So that is all pair of R1, R2, such that R1, R2 is achievable. Okay, so yeah, this definition is not very different compared to the definition of the source coding. Okay, we just have a pair of rate here. Okay, very good. Okay, so now let's take a look at the result. In order to understand the result, maybe let's think about this by ourselves a little bit, right? So let's say if we relax the problem a little bit, right? If we say at the source, we only have one observer, right? That can observe both xn and yn and knows the joint distribution, right? Then the problem will be like a source coding problem, right? So this basically means that we can see easily that R1 plus R2 has to be bigger than or equal to the joint entropy, right? If you consider x, y as a source, right? So we can use the typicality encoding and to achieve this result, right? Easily, okay? So we can use the chain rule of entropy to write this as hx plus hy given x, right? So do you see any implication of this formula, right? So basically, so we can, instead of doing this coding together of x and y, we can doing the sequential coding kind of thing, right? Because so this can be achieved easily, right? For example, by encoding x only by R1, right? And then we fix x, right? We can generate code word for each sequence of y by fixing x, right? So this might be achieved by R2, okay? And vice versa, right? So we can also write this in this way. So we encode y first, and then we may encode x. Okay, so this basically means that by using the correlation between the variable x and y, right, when we do this compression, so basically this is the best we can achieve for a source coding problem, right? But for the second one, we may be able to achieve this, right, by the property of the entropy, which means that the conditioning always reduces entropy. We know this guy is less than or equal to hy, right? Therefore, by knowing the joint distribution between x and y, we can save, right? But that is under the condition where the source can observe both x and y. It knows the joint distribution, right? Okay, so this is kind of the idea, right? In other words, so this might be a lower bound of R1, and this might be a lower bound of R2, right? Or this is the optimal, I mean, this is definitely a optimal point that could be achieved by this distributed source coding problem, right? We cannot beat this one because this can be achieved under the condition where we can observe both x and y, know the joint distribution. Okay, so this could be like the best point we can achieve. The same similarly for this point as well, right? So we could not beat those points, right? But the question is that can that be achievable? Because now we are doing distributed source coding, source coding problem, right? Which means that at each source we can only observe x or y, and then we only know the marginal distribution. So we don't know the joint distribution, right? What can we do, right? Okay, very good. So the theorem, which is called the sleeping wolf coding theorem. Okay, so it's to tell you that this is indeed possible, which is very counterintuitive, right? Okay. The optimal rate region denoted as R star for distributed lossless source coding of a 2 DMS source x, y is given by the following. So R1 will be bigger than the entropy of x given y, right? So this is pretty much like this term. And R2 is bigger than or equal to the entropy of y given x. And then the summation of these two has to be bigger than or equal to hx y, the joint entropy, right? This cannot be beaten. Okay, very good. So this is basically the rate region, right? So now let's sketch it and see what it looks like. So basically, I have 2 dimensions, right? And we can think this is R1, this is R2, and so we have to mark a few important points. Let's say here is hx given y, and here is hx, and here is hy given x, and here is hy, right? And from the result, here we can see because R1 has to be bigger than or equal to that, and the sum of this has to be bigger than or equal to the joint entropy. So it basically means that this point and let's see, and this point, right? Maybe let's mark it more carefully, right? Because this guy plus this guy will be equals to the joint entropy, right? And similarly for this point, this guy plus this guy equals joint entropy, right? This 2 point is achievable. So actually this line is achievable, right? And we say, you know, R1, R2, and the R1 plus R2 are bigger than those points, right? Which basically means that everything here is achievable, right? This is the achievable region of R1 and R2, okay? And naively, if we use distributed, I mean, we can do this 2 source coding using the technique that we learned before separately, right? So this basically means that this point is achievable, right? If we're doing this for x, then we can achieve the h of x. If we do this for y, we can achieve h of y, right? Obviously, anything above here, so that can be achieved easily, right? So the question is, how can we achieve something in between here, right? So that's the tricky part for this distributed source coding. Okay, so okay, very good. So this is for the theorem, and we have a few remarks here. Okay, remark. So it seems extremely counterintuitive, right? Because at one source, we don't know the other source, right? So how can we achieve something like this, right? So that's very counterintuitive, right? The real trick here is that we allow errors, right? Although the error is a symptotic zero, but it's not zero. It's not zero error, okay? So say the rate of lossless source coding. Okay, so if we consider the rate of the lossless source coding, which means that the single source and single destination, so we have seen that we prove that zero source and the symptotic source, they're identical, right? Distribute lossless source coding is the same as that of zero error compression using variable length coding. Right, we have proved that before, right? So we use one length to code the source for the typical in the typical set, and use another length to code the source symbol that are not in the typical set, right? But eventually, the entropy could be achieved for both zero error compression or the lossless coding, right? Lossless here basically means asymptotically zero error. Okay. However, for the distributed source coding problem, this is not true anymore. Okay. The Slepian Wolf coding theorem does not hold in general for zero error distributed compression using variable length codes. Okay, in fact, for many 2DMS XY, the optimal zero error rate region is indeed R1 bigger than or equal to HX1 and R2 bigger than or equal to the entropy of X2 or Y, right? So X and Y. Okay, so yeah, this will not hold in general for the zero error case. Okay, so that's important to notice. Okay, great. So now let's talk about the achievability. And before that, we need to introduce the conditionally epsilon typical sequence. Okay, and let's recall the definition of the jointly epsilon typical sequence. So which is denoted by a epsilon in xy. So that is for the pair of x and y. So the length of each vector is n, right? So such that 1 over ix minus hx is less than or equal to epsilon And similarly, we have this for y, and then for both x and y, we'll remember that I means the self information. Okay, less than epsilon, right? Okay, so this is definition of the joint typical sequence. So the conditionally epsilon typical sequence is as follows, right? That is to fix x or fix y, and then we have what are the other sequence that are in this joint typical set? Okay, so let's write it down. So we let x and y are in this jointly typical set, x and y, right? So because of that, we can derive that x will be in this typical set, will be in the typical set of x, okay? And given this, the conditionally typical set denoted by y given x, so this x is given, right? We observe x, okay? And we know x is in here, okay? Given this, so this is all the sequence of y such that x and y are in this jointly epsilon typical set. Okay, so this is basically the definition of the jointly epsilon typical sequence. Okay, and given that, let's see some property of it. So the most important property that we're going to use later is as follows, right? So we're going to have an upper bound and a lower bound for this guy. And similarly, you can define x given y of this, right? Which is almost identical. So we have an upper bound and a lower bound, right? The upper bound of this is nothing but 2 to the power of n. So you may think that, okay, if there's no this x, so what inside should be the entropy of y, right? But because we are conditioning on the observation of a typical sequence x, so here is x given y, is y given x, okay, at 2 epsilon, okay, and then the lower bound is as usual, right? You can see the technique here, we're gonna prove it would be basically identical as before, right? Okay, so we have 1 minus epsilon here because of the law of large numbers. Okay, so let's prove this lemma. Okay, so in order to prove this lemma, because now everything is like y given x, right? So we need the conditional probability, which is this, right? Let's compute it. So by using the Bayesian rule, we get this, right? And because x and y are in the typical set, and x is also in the typical set, therefore we can have a lower bound for this, right? So this is bigger than or equal to, so on the numerator, we need a lower bound, right, which is 2 negative h x y plus epsilon, right? This is what we learned when we talk about the jointly typical set, right? And for the denominator, we need the upper bound, right, which is 2 negative n hx minus epsilon. Okay, so this is because that x is in the joint typical set, is in the typical set as well, right? And this equals to, so now we can see there's hxy here and minus hx, right? So that will give us 2 negative n h y given x and plus 2 epsilon, right? Because we have epsilon here, we have minus epsilon here, okay? And now we have a lower bound for this conditional probability, right? And similarly, so we can also show that P y given x, So that will be less than or equal to this, right? This is very straightforward. We just need to show, we just need to use a upper bound here and lower bound here, and then we can achieve this, right, easily. Okay, very good. So next, let's show this lemma. Okay, so from this two fact, so we can compute the follows, right? So first, let's consider the upper bound here, right? So we know 1 is bigger than or equal to p, the probability that of this guy, y given x, given x, because we observe x, right? We fix x. So this guy will equals to the summation of all the possible y such that x and y that is in the joint typical set. Okay, and then we compute. So inside should be this probability. Okay, so we just check for each y such that y and x are in the typical set. Okay, so now clearly we're going to use a lower bound for this guy that is obtained here, right? So that equals to negative h y given x plus 2 epsilon, right? And the rest is the routine, right? So now, so this is not a function of y anymore, therefore we just take the cardinality out, right? That equals to the cardinality of this guy, y given x, right? Because that's basically the definition of this. Okay, and multiply 2 negative n y given x plus 2 epsilon. Okay, therefore we get this guy would be less than or equal to 2 negative this, right? We just move this guy to the other side, right? We can get the upper bound of this guy. Okay, and similarly, so we can get a lower bound, right? So maybe I can write this. So here we need for large n, and we know this is less than or equal to this guy. Okay, again, so we're gonna write it down as a summation of this. Okay, and so the procedure will be identified as before, right? So here we need upper bound, right? So that is basically less than or equal to, and we can write this down directly, y given x, and then we have upper bound here, so which is this. Okay, and therefore we can move this to the other side, right? And can obtain that the cardinality of this is bigger than or equal to 1 minus epsilon 2 in h y given x minus 2 epsilon. Okay, very good. So this is the jointly epsilon typical sequences, and with that, so we're ready to show the achievability. Okay, so as we said before, so this achievability needs to use a new technique which we have not seen before, right? So this is called random binning. Okay, so which is different compared to the typicality encoding that we have seen before. Let's recall, right, for the source coding, single source coding problem, so what we do there is that we only transmit whatever is in the typical set, right? So we transmit everything in the typical set, and then that's it, right? That's our encoding, right? We give an index for each sequence in the typical set. Okay, but random binning is somewhat different. So at encoder, we do not need to know the typicality property. Okay, let's see what we do here. Actually, the idea is also very, very simple. So first of all, we're gonna have a number of bins. Okay, so this bin basically means a bin, right? So it's like the binball problem, the bin for the binball problem. Okay, so let be B1, 1, B1, 2. So those are the bins for X. Okay, so we use sub 1 for the indices of X, right? Because the number of indices is M1, right? It means that we need M1 bins, okay? And B2 1, B2 2 up to B2 and 2. So those are the bins for the random variable y, right? And y sources. Now let's illustrate what is the encoding procedure. It's rather simple, okay? So for example, for X, so what we have here is that we have, let's say those are our bins, right? Let's say here is B11, B12, B13, and here is B1, M1. Okay, so what we are doing here is to randomly assign each bin to a source. Okay, so for example, let's say this is our source X, right? That is in this alphabet, right? And so basically, we're gonna randomly assign each bin to this source, which means that in bin 1, so we may have three source sequence, right? Bin 2, we may have 4. Bin 1, we may have 1, and the last bin we may have whatever 4. Okay, so each of this is basically, right? Each of this is a source. Maybe we write this in the other way, right? Okay, so basically we randomly give a bin index to each source. Okay, that's it. And the encoding is very simple. So we just need to transmit the bin index of what we observed, right? For example, if this circle, this ball is our source sequence, and then we just transmit 1, right, which is the bin index, right? If this is our source sequence, we just transmit 3, which is the bin index, right? So the bin index represent the indices that will be transmitted, or the code word. Okay, so this is called random binning. The random part comes from that we randomly assign each bin to a source symbol. Okay, so let's write it down. So the encoding F1 is from this alphabet to 1 to M up to M1. Okay, so what we do here is that we randomly here means the uniformly at random. Okay, we randomly and independently assign a bin index M1 to each source sequence. Okay, and similarly for F2, which is independent of F1. Okay, so we do a similar for F2, and the bin indices transmit for Y. We assume that is M2, right? That is the bin indices. Okay, And after assignment, so for the transmission, it's easy, right? We just, so the encoder just send M1 and M2 if X is in B1, M1, and Y is in B2, M2. Okay, very good. And so this is the encoding, right? For the decoding, so remember that for the encoding, it has nothing to do with the distribution for both X and Y, right? So, and we didn't use any typicality property, okay? So the typicality property will be used at the decoder, okay? For decoding, we need to determine the function of G, so which is from this product set to X and Y, okay, in particular. So the decoding procedure is as follows, right? So now we have, so basically two bin indices, right? And at the receiver side, because this bin assignment will be known at the receiver, okay? So therefore, it means that upon receiving these two indices, M1 and M2, so the receiver can see all the source sequence X and Y in both bits, okay? So the decoding procedure is very simple. It will just find an X and a Y in the corresponding bins such that they are jointly typical. And then that's it, right? So if there exists only one pair of such symbol, then that will be our decoded symbol. Otherwise, it declares error. Okay, so let's write it down. So given the index pair M1, M2, the decoder declares X hat, Y hat to be the estimate of XY if it is the unique jointly typical pair in B1, M1, and B2, M2. Okay. Otherwise, A declares an error. Right. The important thing here is that so X hat and Y hat has to be unique jointly typical pair. Okay. Otherwise, it will not work. Okay. Very good. And in other words, so let's try to draw a figure of it. So let's see. So this direction means X, and this direction means Y. And let's draw all the bins here. For example, okay. So let's see. Here is B1 1, B1 2, B1 3, so on, and B1 M1, and here is B2 1, B2 2, and B2 M2. Okay, and let's assume that so we have a number of source symbols here, for example, something like that, maybe. And similarly for this Y bin, okay, yeah, maybe, okay, something like that. And now let's say, so when we receive the symbol, and we can see that if only for x, maybe those black black dots are in the typical set of x, right? So maybe those are the black dot here are in the typical set of y, for example. However, if we want to see the dots that are jointly typical, maybe there is only one like that, right? This one basically corresponding to this point for x and this point for y, right? And maybe for this point, this is, you know, the one that is in the jointly typical set, right? Maybe here, maybe this one is in the jointly typical set and so on, right? So basically we say, okay, those might be in the jointly typical set, right? And this point is our decoded message or the estimate of x and y, right? If no such point exists, or there are more points in these two bins, then we declare an error. Okay, so this is basically, and by the right choice of the number of bins for x and y, so we can guarantee that there always exists only one point like this with high probability. Okay, so that's basically the idea of random binning. Okay, so now let's try to prove the result, right? So basically what we're going to show is that if we pick M1 and M2 correctly, then the error of probability will go to 0. Okay, so without loss of generality, we just assume that the bin 11 is transmitted or is received at the receiver. Okay, so this basically means that as f1x, we assume x and y are what transmitted. f2y, that is also 1. Okay, very good. And now, based on this design, so we need to characterize what are the error event, right? So the first error event, epsilon 1, is basically the event that, so the event that x and y, both of them, are not in the typical set, right? So if there's no one, if you know that is not in the typical set, then we have to be in error, right? So the second error is that there exists other x denoted as x tilde, right? So that is in B11. Remember that the index 1 is transmitted, right, or is received. Okay, so there exists another x tilde, right? This is for some x tilde that is not equal to x, which is transmitted, right? And such that x tilde and yn, so that is in the typical set, right? Joint typical set. And then we have an error, right? Because x tilde is not what we transmitted. And similarly, epsilon 3 is something for y, right? If y is in this and y tilde, that's not equals to y, however, so y x and y tilde, so those are in the typical set. Okay, then we're also gonna have an error, right? The last error event is that we have both x tilde and y tilde. No, none of them are transmitted, and but they are jointly typical. Okay, so this is, we have this and this for some x is not equals to x and y tilde not equals to y. Yeah, here we need to be careful. So let's write it as random event. Okay. and such that x and y, so both of them are in the typical set. Okay, those are the 4 possible error events. Okay, so you can think whether there are some other error events, right? There should be no. Okay, so now the total error probability here. So here the error is actually conditioning on the bin 1 is received, right? But it doesn't matter, right? So we're gonna compute this error probability, and then if we average over all the possible bins, it'll be identical, right? So you can double check that. So because of the random bin assignment, right? So the probability of error would be less than or equal to the sum of these 4 terms. So this is by union bound. Okay, so now let's compute one by one, right? If each one goes to 0 as n goes to infinity, then we're done for the achievability. Okay. And the first error probability will goes to 0 when n goes to infinity, right? This is straightforward because that's for the typical set, right? So those are not in the typical set. The probability of this will goes to 0, okay, as n goes to infinity. Okay, that is straightforward. So the hard part is E2 and E3, okay? So now we need to compute it. So let's compute it. So for E2, so basically this is the probability that of this event, right? And we can see that for this event, so let's compute the probability of this, right? So, okay, so this probability of that is nothing but, so we can see here the random variable is xn and yn, right? So we need to do a summation of all the possible x and y, okay? And then compute the probability that x tilde is in B11 for some now x tilde not equals to x, and x tilde and y, they are in the joint typical set. Okay. Okay, very good. And next step is to compute this probability. Okay. And this probability will equals to nothing but, so so here we just need to so here, because by this step, so x and y are fixed, right? So here the only thing we need is to find an x tilde to satisfy this condition, right? So we need to sum over all the possible x tilde. Okay, so sum over x tilde, that does not equals to x, and x tilde. So x tilde and y are in this jointly typical set for a fixed y, right? That's precisely the definition of the conditionally epsilon typical set, right? It means that x tilde is not equal to x, and x tilde is in the typical set. It's in the conditionally typical set. Okay, and then now the probability is, so we fix this and we fix that, and the probability is basically x tilde that is in the bin 1. Okay, very good. So we write down the probability. Okay, and this probability is easy to compute, right? This is the reason why we're using random binning, right? Because this probability can be computed easily. So because we're randomly assign each bin to each indices, therefore the chance that this guy is in bin 1 is nothing but 1 over m1 equals to 1 over 2nr1. Okay, and then the rest should be straightforward. So so now we can see that, so this guy equals to sum over x and y, pxy, and then, so the number of items here is the cardinality of this. Okay, and then we multiply 1 over 2 and R1. I believe we need to have less than or equal to here because we need to get rid of this case, right? X hat will not equals to X. Okay, very good. And the next step is that we're going to use the upper bound of this guy that was characterized before, right? So this is less than or equal to this times okay. And now clearly, so this is clear, right? So the summation of this guy is 1, so that equals to 2 to the power of negative n r1 minus hx given y minus 2 epsilon. Okay, and in order to make sure this guy goes to 0, so we need, so this guy goes to 0 if n goes to infinity, if r1 is bigger than hx given y plus 2 epsilon. Okay, and then so we get one part of the achievability region. Okay, and given this, similarly, using, let's say, computing using the exact same approach, we can to compute the probability of E3, then we get R2 should be bigger than hy given x plus 2 epsilon. Okay, so that is identical as this. So the only thing left is to compute the probability of E4. Okay, let's compute that. So again, this is identical as before, right, with very small difference, but to be complete, let's compute it. So we use the same approach. We can write this probability as this guy, right? So the probability is that the event is that x tilde in B1 1, y tilde in B2 1 for some x tilde not equals to x, y tilde not equals to y, and then we have but x tilde, y tilde that is in the joint typical set. Okay. Okay, very good. And next step is to compute the probability of this event, right? Again, so now we're gonna traverse over all the possible x tilde and y tilde, right? This is the summation over all the possible x tilde not equals to x, y tilde not equals to y, but x tilde and y tilde, so they are in the joint typical set. Okay, and the probability here is x tilde is in B11, y tilde is in B11, y tilde is in B21. Okay, and for this probability again, so because of the random binning, right, we assign the bin indices independently between x and y. Therefore, this guy equals nothing but 1 over m1 multiply 1 over m2, which is 1 over this multiply 1 over that. Okay, so using the similar approach, so we can show that this is less than or equal to pxy multiply the cardinality of this guy, the jointly epsilon typical set, and then times 2 negative n r1 plus r2, right? And then we know the upper bound of that, right? Which is equal to 2 n hxy plus epsilon, right? We have shown this a few lectures ago when we talk about the channel capacity, I guess, right? So okay, and clearly this is 1, right? And then we can get this goes to 0 when n goes to infinity if r1 plus r2 is bigger than or equal to hxy plus epsilon. Okay. Okay, very good. And then we can see this goes to 0 when this is satisfied, right? And so now we have all the three conditions, the boundary conditions. Okay, and by doing that, we finish the proof here. Okay, so this is the achievability part, right? So important technique here is the random coding. Okay, okay, great. So now let's take a look at one remark here. So a natural question here to ask is that, so why the distributed source coding and source coding are different, right? One uses random binning, the other one uses the typicality coding. Okay. In other words, a valid question here to ask is that whether this random binning idea can be applied for the source coding, right? The single source coding problem. Okay, the answer is yes. Okay. So random binning can be applied to lossless source coding problem as well. Okay, so the idea is as follows. I'll just briefly describe the encoding and decoding approach, and you can show that the error goes to 0 when r is bigger than the entropy of x easily. Okay, so the encoding part is we randomly and independently assign a bin index, let's say n, that is in from 1 to 2 to the power of nr, to a source sequence x in x to the power of n. Okay, so this is very similar to what we just seen. Okay, and for the and the encoder will just send m if x is in this bin. Okay. All right, very good. And for the decoding part, okay, it's also identical as before, but now we only have receive one bin indices, right? So the only thing we need to find is that we just need to find the unique symbol that is in the joint typical sequence, and we're done. Okay, so this upon receiving m, the decoder declares x hat to be the estimate of x if it is the uniquely typical sequence in this bin. Okay, otherwise it declares an error. Okay, so that's basically the decoding procedure, and so you can see that the procedure is very simple, right? It's even might be simpler than before. So we see, so those are, let's say for example, bin 1, bin 2, bin 3, and so on. Here is bin to the power of nr. Okay, and after this random binning idea, we can see there are a number of source symbols for each bin, right? For example, and so with high probability, we're going to show that if we pick R correctly, with high probability that there will be only one guy in each bin that is in the joint, that is in the typical sequence, okay, like this black dot, okay, and that's basically our encoding idea, okay. So this is the random binning, so which is very important, especially in the network information theory. We're gonna see this everywhere almost, right? Extremely important coding idea, and it's relatively simple as well, okay. So hopefully you'll learn something, although this will not be our final exam. So the very last topic in this class is to prove the converse, okay. So this is more like an exercise of what we have learned before, right? Because the procedure follows the procedure that we introduced exactly almost, okay. So let's try to show the converse part of the Slepian-Wolf theorem. Okay, so we suppose that we have f1, f2, and g, the encoding and decoding function. Okay, so that satisfies the Slepian-Wolf coding criterion, okay, with small error, with the error probability epsilon. Okay, so clearly we're gonna use that, use the funnel for this guy, right? Okay, very good. So we need the error to be small. Okay, so now we need to show three equations, three inequalities basically, right? So let's show the first one, NR1, okay? So we only need to show two inequalities, right? Because R1, R2 will be identical, okay? So let's use the the normal procedure here. So we write this as log m1, right? And then we notice that we need a lower bound, right? So this would be bigger than or equal to the entropy of fx. Okay, so this is because of the cardinality bound, right? We always use that. Okay, so the new part here is that we need to introduce y. Okay, so the way to introduce that is also very straightforward. We just use this condition on y, because that is something we want, right? Want h of x given y, right? Okay, and so this is a new step. Okay, after that, everything will follow exactly as what we have seen before. So next step is that we're gonna make the mutual information term, right? Which means that this we need to minus h f x1 hat given xn and yn, right? So we need the xn there, right? Because we want hx given y. Okay, and clearly this entropy term is 0, right? That will not change the equality sign. Okay, and then we get a mutual information between between x in and f1x given yn. Okay, next step is to write this mutual information in another way, so which is hxn given yn minus hxn given x1 xn yn. Okay, very good. And okay, we're almost done, right? So next step is that we do not want this guy. Okay, so we want to get rid of this guy, and the way we're gonna get rid of this guy is that we're gonna use funnel, right? But in order to use funnel, so we need f1 xn. We also need f2 yn, right? Because we have to observe both of them to do the decoding, right? Therefore, what we want is that we want to put a f1xn and f2yn here. Okay, so if that be okay, right? It'll be okay, right? The reason is that we know yn, so we know this, right? We're adding a term that for free basically, right? Because we know yn, and the f2 is a function of yn. Okay, therefore we'll have an equal sign here. So okay, and clearly this will be less than or equal to n times epsilon n, right? Because of Fano. Okay, because we assume those are sleeping wolf code. Okay, very good. And because of that, and we can see clearly that the next step is that, so this will be bigger than, okay, and then this equals to n h x given y minus n epsilon n, right, because of the DMS, right? Okay, therefore we get R1 is bigger than or equal to h x given y minus epsilon n. Okay, and this is the first inequality, and similarly we can show that R2 is bigger than or equal to hy given x minus epsilon n as well, right? You can see this should have the exact same form. Okay. Okay, so the last inequality we need to show is the last one, R1 plus R2. Okay, so again, so the procedure of that is almost identical here. So n times R1 plus R2. So I want to lower bound that, right? That is equals to log m1, m2, right? And clearly that is bigger than or equal to h f1xn f2yn, right? And next step is again identical as before. So this is even more typical because we do not need to introduce the condition here, right? We just need to make try to make the mutual information term come out, right? Okay, and then so clearly this term is 0 because f1, f2 are functions of x and y, right? This is the mutual information between xn, yn, and f1xn, f2yn, okay? And then we need to write the mutual information in another way. Okay, and clearly this can be upper bounded by n times epsilon n because of the Fano, right? Again, here's Fano, and then we get this is bigger than or equal to hxn yn minus n epsilon n, so that equals to n h xy minus n epsilon n. Okay, therefore we get R1 plus R2 bigger than or equal to this guy minus epsilon n, where epsilon n will goes to 0 as n goes to infinity. Okay, so we're done for the converse. You can see the converse is relatively straightforward, but in general, in network information theory, the converse is extremely challenging. So this, we need lots of tricks to do that because the network is more complex. Okay, great. So this is the very end of this lecture. Okay, so although our semester is over, it doesn't mean that so we don't want to learn more about information theory, right? As you may know that I'm uploading more videos to my YouTube channel, right? So if you are interested in other topics, please let me know. So I can, continue uploading other videos for other topics in information theory that you are interested. Okay, please let me know. Okay, and so please let me know if you have any other questions or comments. Please stay safe and healthy. So I'll see you in the final exam. Good luck. See you. Bye.